Why VFDs? Can anybody tell me why we're looking to use VFDs? The main reason basically is energy savings. Why? If we're using an example for a standard application where we are controlling a flow, by example, okay? The classic one will be with what? So we have a motor that is powering a pump, the pump is pushing the flow, okay? How are we controlling the flow in that case, in a classic way, without a VFD?
Dampers.
With dampers, inlets, all kind of mechanical gear, okay? Is that efficient? Not for the motor. Why? Because the motor is going to work always at the full speed and it's going to take the full amount of power required, okay? Now, if we're using a VFD, instead of that, we can actually control the flow by controlling the speed of the motor. So we don't have to run the motor at full speed all the time. So it's all about saving dollars, okay? Now, when we're trying to look at VFDs, we have to look at multiple things, okay? So what we came up with an acronym, you know, that is illustrating a little bit what we have to look at when we're trying to pick up a VFD for a certain application, okay? And we're calling that a backpack. It's easy to remember. B, basic AC motor and drive theory design. So this will be your, and think about this backpack, it's exactly like when you're packing an actual backpack. You will have to put everything in there so it's as balanced as possible, okay? So you're starting from the base of the backpack where you're putting whatever it's more heavier, you know, the basic stuff, and you're going up and adding all kind of other things like accessories and so on, and you will see. So in this case, for our base, it's going to be this basic AC motor and drive theory, okay? A, application evaluation to determine drive size and performance. C, for control scheme for analog, digital, IOs and communication and so on. P is for protection, process, motor, drive and line. A, ambient environment, pollutants, temperature, moisture. And C, it's going to be commissioning and integration, okay? And we're going to touch on each of these ones today. Now, for the basics, everybody knows how the electric motor is built, okay? So we have our motor frame, some wiring covers, stator, rotor, and belts, okay? It's pretty standard. Now, how the motor is working, basically, when we're passing the three-phase through the windings, basically, we will have a magnetic field that basically will push the rotor, so it's going to rotate and will create that motion. Okay? Three-phase applied to the stator winding, rotating magnetic field is created. Okay? The speed of the rotating field, it's going to be called your synchronous speed, okay? And we have a formula to calculate that. It's pretty straightforward. It's 120 multiplied by your frequency and divided by the number of poles. Now, the frequency here in North America, we're using 60 Hertz, okay? So it's pretty straightforward. Number of poles, what can we have for poles for a motor? Is number of poles. So, the speed, in this case, is going to be influenced mostly by the number of poles that we have, okay? Higher number of poles, how it's going to be the speed? Higher or lower? Okay? More poles, less speed, okay? Now, if we're changing the frequency, we can also change the speed, because in the formula, if we're looking, it's 120 multiplied by frequency and poles. Now, the motor is already built. We have 2 poles, 4 poles, or 6 poles, so we cannot play with that anymore. So what we can play with is the frequency in this case. Okay, 10 Hertz is going to be slow, 30 is going to be faster, 60 is going to be the synchronous speed. Okay. Now for the same formula, 2 poles, 4 poles, 6 poles. Okay. We are going to touch this, but what do you think on a real motor? Is this what are we going to see on the nominal plate of the motor? Are we going to see 3600 RPM for a 2-pole motor? What do you think in a real life? Real motor? Less. Any idea why? We're going to touch a little bit on that, but...
Sleep ratio.
Okay, so we have the slip. Okay, so in an ideal situation, your rotor will rotate at the same speed with the magnetic field created, okay? But we have some losses, okay? Who do you think is causing those losses in the motor? Why it's not rotating at the same speed with the rotor? What's that? Okay, you have some losses in the windage, right?
Okay.
Come on, don't be shy.
Okay.
Bearings, so you have some frictions in there. So there are all kind of things that influence that. So we will never have that speed. So all the time on your nominal plate, you will see something a little bit lower than the calculated speed. Okay, and who's going to calculate that? Basically the manufacturer of the motor. So they will measure that, and depending on how well it's the motor built, you will see something close to that number or something a little bit far from that number. Okay, the higher the load on the rotor shaft, the more the rotor will slip. Okay, so okay, we touch. So the actual speed will be your synchronous speed minus that slip. Okay. Now, let's introduce a little bit the torque. So measurement, of course, of rotational force. I don't think that I have to explain too much to the engineering side on that. You're pretty familiar with this. It's the ability basically of that rotating element, you know, gear, shaft, or whatever you have to overcome that turning resistance. And the torque requirements will be considered when you're selecting your drive. Horsepower, unit of measurement. Okay, so these are just some basic formulas, and we just put them there so you know what we are talking about. In order to rotate that motor shaft, basically under a specific load, that motor will need to convert that electrical energy to a mechanical energy. Okay, and the horsepower rating of the motor will be actually the amount of the power that you need to provide the torque required by the application in order to maintain your motor's nominal motor's nameplate speed value at full load. Okay. This is a little bit more developed. So if we're replacing the wattage in the horsepower formula with what the actual wattage means, you'll get something a little bit more evolved. And based on these formulas, you see what we can play in order to adjust certain elements like the speed of the motor. So if we're looking at this formula, what do you think we can touch in here in the influence? Mostly voltage and amperage, basically. Okay, the rest are pretty standard. Okay, this is the torque speed curve for a standard NEMA B motor. Why NEMA B? Because NEMA B, it's probably the most used motor on North America. Okay, so if we're looking at this, we have our locked rotor or stall torque. So this is where our motor is starting at 0 speed. Okay, so in order for us to start the motor, we have to break that. Okay, once we're starting, you have pull-up torque while the motor is speeding toward the nominal speed, and you're getting in the pull-out or breakdown torque when the motor is getting close to what the nominal speed is. Okay, and you will have your full load torque at pretty much the nominal speed. As you can see, it's not exactly 1800. Why? Because of your sleep. And remember, we already said that. Okay, between here and here, you have your slip, okay? And for us, really, that's what Doug was saying earlier. This area where your slip is the area where we can play. The higher the efficiency of the motor, the shorter interval we'll have for that slip, so less room to play with the VFD and the motor. Okay, so this is pretty much the standard curve. Now, if we're looking, this is what I was saying, we have a couple NEMA designs for the motor. There is a NEMA E, which is not here, but this is mainly what you have, NEMA A, B, C, and D. You see all the difference between this. If you have, let's say, an application where you're demanding a lot of torque in the initial, when you want to start the motor, you know, like a big flying wheel or something like this. Which motor do you think will handle better that situation without having a VFD? D. That's correct, okay? But D, it's really expensive. It's, I think, about 2 or 3 times more expensive than a NEMA B, okay? So it's not very good solution in most of the applications. Now, with the VFDs, we don't really need this because the VFD can control differently how the motor is starting, so it's going to help with that. So that's another good reason to use the VFD. Okay. Now, how did they build the algorithm and the theory behind the VFD drives? They took the motor and they translate that into an electrical circuit, okay? So if we're looking at our motor, it's going to look pretty much like this in a electrical diagram, okay? So you're going to have your stator, you're going to have your rotor, okay? You apply voltage at the motor terminals, you have a current flowing through the stator, you have the resistance in there, you have the magnetizing voltage, okay? So they looked at, I'm not going to insist too much, but they looked at all the elements involved into this, and they translated that into an equation that can be used in the algorithm control for the drive, okay? For us, the ability to produce that torque, basically, it's going to be proportional with the wattage, okay? This is the formula, remember, for the wattage, volts multiplied by amps, times 1.73 efficiency and power factor, okay? And the applied voltage will be determined, of course, by your source, okay? The amps, it's going to be applied by your total voltage and the total impedance of the motor circuits. What do you think it's forming the impedance in a motor? Do we have capacitance in there? Okay. What kind of capacitance? Between different elements of the windings, basically, because you have an air gap, okay? So you have some capacitance. Resistance, of course, in your windings and stuff like that. So these are the elements, basically, that will contribute to that. So the whole idea of this is just to know that in order to build that algorithm that is embedded in the drives, we needed to look a little bit more deep into the theory of the electrical circuits, okay? And we translated basically the motor into that, they actually, not we, but let's move on to our drive. So we have our motor, we basically, so what we have to do with our motors. Now, the drive. Drives mainly are built from couple main elements, okay? You have your operator controls, which can be, I don't know, your keypad, it can be an HMI through a communication or something like that. You have your control unit, you have your power conversion unit, and at the output, of course, you have your motor, okay? Most of the times with the drives, you have 3-phase in, 3-phase out, okay? Is that all the time? Can you have 1-phase input? Yes, you can. Can you have 1-phase output? Actually, Yes, we can. Now we have the DA1 drive, which basically, the DC1, sorry, which can do single line input, single line output. Okay, so we can control actually some of the single line, single phase motors that are out there. Okay, with the previous drives and most of the drives that are available, we can do single phase at the input, but always three phase at the output. And most of the time when you have a three phase drive and you're using a single phase on the input of the drive, you'll have to derate that drive, and sometimes you have to add some extra capacitance, okay, on that. But now this is the important thing to know. We have a single phase to single phase drive, okay? Now, if we're looking at a little bit farther into our drive, basically we will have our input line voltage, we have our rectifier, we have our DC bus, and we have our inverter at the output. So what we're doing basically, we are taking the three phase, okay, input, we have our sine wave, we transform that into DC, and at the output we have the inverter that will produce what is called a pulse width modulation. Why we're doing this? Why are we converting? Why are we not taking that AC and do something with it? We can't really change the frequency indeed on that. So by converting that to DC and after that through the inverter into a pulse width modulation signal, we can play with frequency, you know, playing with the amplitude and stuff like that. If we're looking at our converter or rectifier section, and you will see, you'll find in literature this called both converter and rectifier. Truth be told, the output inverter basically it's also a converter, okay? Because if you're thinking converter, design something, you're converting from AC to DC or from DC to AC, okay? So sometimes in literature you'll find the input rectifier called also a converter, okay? So it's nothing wrong with that. Rectifier basically is just most of the time it's a 6 diodes bridge, which will take your AC and convert it into DC. Everybody knows how a diode is working, so it's either allowing or not allowing the current to pass through. Okay, so depending on where your input phase will be, it will let or not the current to pass, and that's going to create your DC voltage. On some drives, you'll see we can have more than 6 diodes on the rectifier, or on some of the drives we can even have IGBTs that commonly you find them on the output, but if you want to put back in the network when you are in a regen mode, we are using IGBTs to let the current flow in the other direction too. So basically it's becoming an inverter, okay, at that time. Okay. Precharge circuit, this is standard with most of the drives. Why do we have a precharge circuit? On the DC bus we have capacitors, okay, which are here, and we will touch a little bit later about them. Capacitors, usually when you're starting the drive, they want to do what? To suck a lot of current, okay? They're very, very hungry. If you let that, you'll have a big inrush current, okay, which can damage your rectifier. So in order to temperate a little bit what the capacitors are sucking in, you are using this precharge circuit, which basically it's a resistor connected in series on one of the branches of the DC bus, okay? Once the capacitors reach a certain level of charging, then we're closing the contact that is going to bypass your resistor, okay? Usually with the drives, you will hear whenever you power the drive, you're powering up the drive, you will see you'll hear a click, okay? That click, it's actually that contactor that basically it's closing and it's bypassing the resistor, and that's when you will basically get your ready signal for the drive, okay? Till that is not closed, the drive will not be able to operate, okay? Very important. Some people I know, electricians in the field out there, you know, they like to connect and disconnect the drive. If you're doing that too fast and too often, you're going to burn that resistor. Most of the time, that resistor is basically directly on your PCB board, okay? It's not easy to replace, so sometimes you have to replace the entire board just because of that. Okay, we have our DC bus capacitors. They are basically there to provide a little bit of extra energy when it's needed, okay? So if your application is demanding at a certain point a little bit more, you know, in order to avoid any inrush, and because the rectifier will not be able to provide that as fast as possible, you have those capacitors that will basically help a little bit. In the inverter basically is built with IGBTs. There are again 6 of them. The nice thing with IGBTs is that you can basically control both when it's open and it's closed, you know, and you have a higher switching frequency on them. Okay. Also, on some of the drives, on some of the smaller frame sizes, we're offering this, by example, as a standard option. On some of them, it's just an option. The motor can be a motor or can be a generator in some situation. When it's a generator, it's going to push all that energy that generates back onto our inverter. If we're not burning that energy, that's going to basically hit your DC bus. If you're hitting your DC bus a lot of time with that, your IGBTs will not handle in time. So you want to burn off that energy. How? You have basically a 7 IGBT, in this case, that basically when it feels that you have some energy put back, it's going to burn that through a resistor. So it's going to just produce heat. On some of the drives, like I said, instead of having a breaking, you can regen back into the grid by using SCRs or IGBTs on this side. Okay. This is how your pulse width modulation is looking, and this is how we kind of try to recreate that sine wave at the output of the drive. It's not an ideal sine wave because it's pretty chopped, and we can see in here. So we have different durations for the inputs when we open or we're closing the circuit. And based on that, you're creating something, you're trying to simulate basically that sine wave. Higher the switching frequency, a little bit more nicer sine wave you will have. But higher switching frequency, not very good for your motor, because think about this, you're just opening and closing, so it's not that ideal perfect sine wave, so you basically just open, shoot into your motor windings, close, open again. So the faster you're doing that, the worse it's for the motor, and it's gonna start to heat up, okay? And this is how your typical PWM voltage and current waveforms are looking like. So you see it's not a very, very nice sine wave, but it's working, okay? How efficient is your VFD? They're pretty good actually these days, you know. And the amount of losses that you have on a VFD, basically, they're very small compared with the savings that you're doing in energy by using a VFD, okay? Why you have some losses in the VFD? Because we have all kind of electronic involved, okay? We have some resistance in there that is gonna just burn off some of the energy. So there are some fixed losses, you know, which are a very, very small amount of the total power transfer. Usually we're about at 98.5% efficiency, you know. That can vary, but that's pretty much. So it's really, really low, okay. The losses, of course, you have your control logic, you have your cooling fan. This is one of the biggest loss probably, but even for that we have options. We can have the fan to run only when the temperature reaches a certain value, and on bigger frame size drives, basically, we have fans that have their own little small VFD, okay? So they're not going all the time at the maximum speed, but they're also speed controlled, okay? Conduction losses, proportional to your current flow, and you have your switching losses into the IGBTs, okay?